If you don't like the road that you're walking on, start paving another one. Today, we're going to do a Unit 2 practice test. And Unit 2 is about forces. So, we're doing a force practice test in reality. Okay. So, a book sits perfectly still on a flat horizontal table. Which statement accurately describes the forces acting on the book? Well, it's perfectly still, like still water, which means that it's not moving. And that doesn't mean there's no forces acting on the book, because there's still gravity we have to think about. And there's also a normal force. And they cancel each other out because it's at rest. So the table exerts an upward normal force equal in magnitude to the downward force of gravity. Question 2. A car is traveling east down a straight highway at a constant velocity of 110 kilometers per hour. What is the net force acting on the vehicle? So this one is actually a trick question, because where's the trick? It's right here. A constant velocity of 110 kilometers per hour. Like sometimes you could look at this and think, oh, maybe there is a net force acting on the vehicle. But if velocity is constant, what do we know about acceleration? Acceleration would be equal to zero, because velocity is not changing and acceleration is the change in velocity. Therefore, if we look at this equation, net force is equal to mass times acceleration. And if acceleration was equal to zero, this would be equal to mass times zero. And it doesn't matter what mass is. If acceleration is zero, then net force is equal to zero. So the answer is A. A heavy crate requires 500 newtons of horizontal force to start sliding across a warehouse floor. So let's draw this scenario. Honestly, it doesn't really matter, but I'll draw it. And imagine we were pushing it with what? With 500 newtons of force to start sliding. So this means that there is a static kinetic force, static force of friction of how would you say this? Force of friction, kinetic, static friction. I don't know. Like this, right? Force of friction would be equal to 500 newtons, but it only takes 350 newtons to keep it sliding at a constant speed. So that means that our kinetic friction would be equal to 350 newtons. Now, I just wrote this down because I didn't really need to write it down, but it's just to let you know that pretty much always the frictional force, um, its maximum static frictional force is greater than the kinetic frictional force. And that's just something that happens. For example, it takes you more energy to make a couch. Like if you're pushing a couch, it would take more energy to make it start moving than for you to keep it moving against the carpet or something. And this is the same idea. And this is because static frictional force is greater than kinetic force. When this is a maximum? Because static static frictional force, it's more like it changes, because if I apply 100 newtons to this box, then there would be also 100 newtons of frictional force pushing back. There wouldn't be 200, there wouldn't be 500, it would only be 100 newtons of force, because we have to keep it balanced to keep it at rest. So if I push on this box with 300 newtons of force, then frictional force will be pushing back with 300 newtons. It changes with how much I push it. And this means that this one, static friction is always greater than kinetic friction. The other ones don't make sense. Like gravity, this doesn't make sense. Gravity stays the same. The mass of the object decreases once it becomes moving. That's just not true. and this one is not true. Okay, now we're moving on to questions with calculations. So, question 1 is about elevators, and we actually had a test on this, and it was pretty cool. So, let's start by drawing a free body diagram, because that's what we always need to do. So, if we were looking for the student, if we were just analyzing the student, this means that we're not actually looking inside we're not looking at the elevator, we're looking at the student. So we can just draw the student as this dot. And there's a gravitational force acting down on it. And there's also a normal force, which is the scale or the elevator. He's standing on a scale, which is on an elevator, so that's the normal force. And so one thing we need to pay attention to is the scale reading is normal force. And this would be in newtons, not in kilograms, because we're looking for the weight, not the mass. Mass doesn't change as you go from planet to planet, but weight does. Because weight is a vector, I think. Okay. And let's start with the first question. The elevator accelerates upwards at 2.2 meters per second squared. So net force is equal to mass times acceleration. And why did I write that? I didn't need to write that. Net force is actually the sum of all the forces here, which is normal force and gravitational force. So net force is equal to normal force plus gravitational force. And we're looking here that the net force would actually have acceleration of 2.2 meters per second. And because net force is equal to mass times acceleration, this would be mass times acceleration, which is equal to 65.0 kilograms times, and I forgot my Rosetta again. So going upwards is positive, while going downwards is negative. And now this means that because it's accelerating upward at 2.2 meters per second, we can just write it as positive. And we're trying to find normal force, because that is our final scale reading. And we already have the force of gravity, which is just mass times gravity. And that is 65 times 9.81, which is the trusty calc. 637. One second. It's actually negative gravity, because gravity is going downwards. The force of gravity always points down, and in this Rosetta here we stated that going down is negative. So we minus 65 times 9.81, which is negative 637.65 newtons. Now we isolate for normal force, which gives us 2 plus this, giving us 780.65 newtons. Great. So that's our final answer, but we want to round. So there's 3 sig digs, so that's 781 newtons. Now the elevator travels downward at a constant speed of 4.5 meters per second. Trick question. Constant speed. Whenever you see constant speed, the alarm bell should be ringing. Ring, 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 ring. Okay, and because it's at a constant speed, there's no acceleration. So the net force, the normal force would just be equal to gravitational force. Net force is equal to 0. So force and gravity and normal force balance each other out. So that's just his weight times gravity, which is 637 638 newtons. We're calculating for the scale reading. Remember that. And if it was falling, this is actually the same. No, this is not the same thing. Because as it's falling, what would have changed? If it's falling, then our free body diagram changes because there's no more normal force. The only force acting on the student in the elevator is the force of gravity. That's just how free fall works, right? So that would mean that the student has no scale reading, 0 newtons, because it's just force of gravity pulling it down. Those are some pretty important things to pay attention to. Next question, friction at an angle. So let me drink a water. A worker pulls 24-kilogram box across a flat horizontal floor using a rope. Let's just draw the situation and then we'll draw a free body diagram. So there's a box that's pretty heavy. I don't think I would be able to lift 24 kilograms. Could I? 24 kilograms is... The conversion for kilograms to pounds is actually 2.2, I believe. So could I lift 53? I could lift 53 pounds. But like, it would be hard. I'm not that strong. Okay. The rope pulls with a tension force of 115 newtons at an angle of 30 degrees above the horizontal. So there's a rope pulling with 115 newtons. And coefficient of kinetic friction. Oh, that's how you can draw it. No, never mind. The coefficient is always written as mu. Mu. I just mogged you guys. Okay. So A is to draw a free body diagram. So let's do that. I kind of already did that, but I'll do it again with better drawing. And you can just draw like a floor. Doesn't really matter. You can include this part of your free body diagram. And here, as usual, there is a force of gravity and there's a force of normal. But one thing we must remember is that because there is a string also pulling, force of tension, and this has 30 degrees above the horizontal, so 30 degrees. Because there's a string pulling at an upward angle, our gravitational force and our normal force, they are not equal in magnitude. And remember, there's also friction force, because that's what the question said. Now, what does B want us to do? B wants us to calculate the normal force acting on the box. So, in order to do this, I need to take a look at all the numbers again. So there's 24 kilograms, mass equals 24 kilograms. My screen's a bit small, so I can't fit it all. And force of tension is 115 newtons at 30 degrees. Okay, and kinetic friction to 0.210, right? Good. Now, I'm kind of tired. So one really foolproof way of doing this is with a table. So you can just draw like, where do I do this? I'll do it here. X and Y. So you can put your X on this and your Y is like that. And you can, by drawing this table, you get a really nice visual way to calculate all your forces. So there's 4 forces in total, so I made 4 little slots for that. I need 5 slots. Oh, I don't have enough space. Maybe I'll zoom in. That's the strategy. Yes, that is what we want. And then I'll just draw a bit onto the next one. Yeah. So first one was force of gravity. And force of gravity was going down, so this only affects the y-axis. We know that this will be 0. Now force normal, also this only affects the y-axis, so this will also be 0. Force tension, well, this affects both the y and x-axis, but it's going at an angle, so we can't say zeros for this. And oh my god, I need another one. And there's a force of friction. Force of friction, again, it only acts on the x-axis, so there's a y here. And for the last row, we just do a sum of all our forces, x, y, on the x and y axis. Okay. Now where do we go? We can easily calculate the force of gravity. Just 24 times negative 9.81. Again, we need a Rosetta. Oh, I can't. That's kind of out of the camera. Like this. So that's negative 235 newtons. Now, our normal force, we can't find that immediately. We need to calculate that with the force of tension. Also, I need to read the question one more time. Okay. And force of tension, let's look at the x-axis. There's a 30-degree angle, right? And we know there's 115 newtons. So our x-axis would be 115 cosine 30, which would equal 99.5 ... newtons. And our y would be 115 sine 30, which would be 57.5 newtons. And one thing we know, actually I forgot another 0. In our sum, in our net force, y would be 0, because the box is just moving. Like, the rope is pulling the box, but the box is not moving up. It's only moving side to side. So that means that there's no net force acting on the y-axis. So this should be 0. And therefore, this table works out really nicely, because now we know that this sum of all the y values must equal to 0, which means that normal force, this would mean that negative 235 ... newtons plus 57.5 newtons plus normal force should equal to 0, which means that normal force would be equal to negative 230, like, oh, I'll just write it. I guess I'll just write it. It would be 235 newtons, minus 57.5, which is equal to 177.9 newtons. So 177.9 newtons. Okay. And the last thing to check here is, what is our force of friction? We're trying to fill out this whole table, right? And there's one really handy formula, which is that force of friction is equal, also there's like absolute, doesn't really matter, okay, is equal to mu times normal force. And this is equal to 0.2 times 177.94 newtons, which is equal to 0.37. Voila. And this is also negative because we can use our brains here and see that friction is going in the opposite direction. So this is negative 37.3 newtons. Always make sure to get your signs correct, because if you don't, that could be problematic. Now the only thing that's left is to find our net force of our x. So let's add negative 37 and 99.5, which equals 62.2 ... newtons. Great. So we have solved everything else. We already found the normal force, which is 177.9. So that's actually just 178 newtons. And the kinetic friction force we found was 30 magnitude, so that's 37.4 newtons. And the horizontal acceleration, well, we found the net force, right? And that was 62 point something, 62.2 newtons. Our net force. Oh, force net. And that's equal to mass times acceleration, so ma equals 62.2. That means that 24 kilograms times acceleration equals 62.2 newtons. Acceleration equals, can you still see this? Okay, you can. Acceleration is equal to 62 divided by 24 equals to 2.59 meters per second squared. Great. 2.59. Okay. And this is 3, yeah, this is 3 significant digits. Inclined planes. Now this is like, I guess I would consider this like one of the harder ones of this unit, of unit 2. It's just a little more, there's some extra steps. I'm gonna drink some more water. I'm so thirsty. Okay. So, inclined planes would just mean that, blocks on ramps. I'll give you a second to read that. I'm reading it too. And what do they want us to do? They want to calculate the component of gravity pulling the block parallel down the ramp. Now, in order to do that, we have to draw a free body diagram. So, let's first start with a Rosetta. Oh, I'll do that later. A free body diagram. So, let's draw this wooden ramp. Okay, I'll just draw it. No. Yeah. This is a ramp. No. I'll color it brown because wood is typically brown. I don't have brown. What? Oh, I do. Do I? Grrr. I don't have brown. Do I have brown? I do have brown, yes. Technology. Okay, this isn't helping anyone. Okay. And there's a block on the ramp. So we're trying to see if this block will slide down the ramp. This is our final thing, right? So we can just assume that right now it's at rest. Like for this moment. So there's gravity. And normal force is actually just perpendicular to the surface the object is resting on. So it would look like this. And force of gravity is going this way, but there's actually, we can split gravity into its perpendicular and parallel components, because gravity's going down this way, but that's not easy for us to think about because it's on a ramp, right? Gravity is actually pulling the block. Like there's other forces of gravity. There's one parallel to the ramp. 1 second. Dashed. Whoa. Wait, I'll do dotted. Dotted line. Dotted line. Yeah, wow. And there is a... Oh, I should have made my other one a bit longer. It's fine. This is how I typically like to do it. I just draw my arrows like this. And how much was this angle? This angle was 25 degrees above the normal, the horizontal. Okay. Just making a bit of space. 25 degrees. Okay. And so these dotted lines I have drawn here, this is the force of gravity parallel. This is parallel, because you can see they're two parallel lines. This is perpendicular, because you can see they're two perpendicular lines. Oh my god, I spelled it perpendicular. And this is perpendicular. This one is force of gravity perpendicular. And there's also, because we see that force of gravity is trying to pull it down this way, that means that the frictional force is always opposing that force. Great. And now what we have to do is draw Rosetta. So here, because we're looking at this on a ramp, we would actually draw Rosetta sideways, like this, with more straight lines. And so if this block was going upwards, like away from the ramp, I would say that that's positive. And if this block was going higher on the ramp, I would also call that positive. But also, like, this is to your own choosing. You can choose which way is positive, which way is negative, as long as you state it. Okay, and now what do we do? Now we gotta do the calcs. Calcs is short for calculations. It's a lot. I'm gonna write everything down first. Mass equals 12 kilograms. And the ramp is 0.15. So, what? Yeah, kinetic friction. So, goes 0.15. And let's do A. What is A? A is asking, calculate the component of gravity pulling it down the ramp, parallel down the ramp. So that should be easy enough, because let's first find force of gravity itself. That would be mg, which is equal to 12 kilograms times negative 9.81 meters per second squared, which is equal to negative 117. Now if we want to find the parallel component, we should notice that this is a triangle. This part is a triangle. And if we look at triangles, there's a smaller angle, I would say 25 degrees looks more like this. And say the box of this small dot, and we know this is 25 degrees. Now if we were going down, we want to find the the components of gravity here, and actually because of triangles, this would also be 25 degrees. This is not looking clear at all. Let me draw. This is a gravity triangle. A gravity triangle. And this is a force of gravity. This one would be 25 degrees as well, because if we looked at triangles, more deeply, it's really nice. Like, even though it is like it's pretty straightforward, I would also say it's a really nice like idea, because if we knew that this angle is 25 degrees and we drew a thing straight down, we would know that this is 90 degrees, right? And wait, what am I saying? I don't and then I appear to have made a mistake, because I was doing some dumb things. So if we are drawing a triangle like this and you're trying to make a gravity triangle, of course gravity is going down, right? And if we were going to draw our parallel like this and our perpendicular like this, then of course this would be 90 degrees, and this would be 90 minus 75, which would be 65 degrees, yeah. So this would be 25 degrees, because out of muscle memory perhaps, I just remember this angle being 25, but that's only, of course, that's only if you draw your triangle like this, because this would be your perpendicular and this would be your parallel. It's tomato. They both work. And what we're really trying to do is just to calculate each component. So force of gravity parallel would equal, well, we saw that here. Which one's parallel? This one's parallel. Parallel, this would be, if we knew that this was 65 degrees and we know that this long one is negative 117.72, that would just be negative 117.72 cosine 65, which is equal to 0.72 cosine 65, 49.75. Now for the perpendicular component, that would be sine 65. And it's always just either cosine or sine. So that's 65. Whoa. Oh. -106, negative 106.7. 7 newtons. So we got A. So that is pulling the block parallel down the ramp. That would be the first one we got, which is negative 49.75. 8 newtons. Now calculate the normal force. Sure, I will. Normal force, because it's resting, right? And because it's not going like anywhere on the perpendicular axis, this would mean that force gravity perpendicular is equal to force normal. So, like in magnitudes, of course. So force normal is equal to 100 and 106.7 newtons. Now, because it's three significant digits, they would want us to round to 107 newtons. But I'll just leave this here because 6, 7. 6, 7, 6, 7, 6, 7. Determine if the block will slide down the ramp. How do we do that? Well, we have to calculate our friction force. Yay! Friction force is equal our mu, 0.15, times our normal force of 106.767 is equal to 0.15. And because this is going in the opposite direction, we've got to make this negative. Oh, we're making this positive, actually. Be careful. Yeah, because we're going, if we look at this Rosetta, force of friction is going in the positive direction. It's keeping it up the ramp. So this is actually 16 newtons. Great, we found friction force. And now we just got to connect this with our other thing, because friction force is 16 newtons, and we want to find the net force on the x-axis, or the, it's not the x-axis, it's the parallel axis, which is equal to force of friction, 16 newtons, plus force of gravity on the parallel axis, which is negative 49.75. Well, by putting it like this way, it's pretty obvious that the gravity wins out. And negative 49.75 plus 16, that gives us 33.75 newtons negative, which is equal to negative 33.8 newtons. So the block will slide down with 33.8 newtons of force. And we're trying to find the acceleration. Wow. There's many components to this question. I'll do it up here. So that was our net force, 33.8, which is equal to a mass of 12 kilograms times acceleration, right? And this divided by 12 gives us an acceleration of negative 2.8. 2.81. Great. Last question. Are you guys tired? I'm very tired. I didn't study at all today, but I'm still really tired. A 4.5 kilogram block sits on a rough, flat, horizontal table. It is connected by a massless string passing over a frictionless pulley to a hanging mass of 2.5 kilograms. The coefficient of kinetic friction over the horizontal block on the table surface is 0.18 meters. Okay. Calculate the force of friction acting on the horizontal block. So this is also a very, very typical problem. If we have a table here, and we have a mass, and there's a string connected to this mass. There's a small roller here. I get this is called a pulley. Yeah, not a roller. It's called a pulley. And this is my string. Actually, I'll get a new color. First color we used in this video. So our string is red. Okay, and there's a hanging mass. In order to solve this problem, we need to look at both components, like the system as a whole, but also each component of the system. So let's do that. We're trying to calculate the force of friction, but in order to do that, let's first find, will it move? So the 4.5 kilogram block Mass 1 is equal to 4.5 kilograms. Mass 2, which is the hanging mass, is equal to 2.5 kilograms. And our mu is equal to 0.18. And first, to find the friction, we need to find the normal force, which is equal to gravitational force. So normal force is equal to mg, which is equal to 44.1 newtons. Honestly, like, you can also draw your free body diagrams, but once you practice enough, it's not very necessary. I'll just draw it anyways. But this is of the block on the table. There's normal force. There's gravitational force. There's normal force. And there is a force of tension. Now let's find friction, which is equal to 44.1 newtons times 0.18, which is equal to negative 7.95 newtons. Okay, so we found friction. Determine the acceleration of the whole thing now. So we can think of this thing as like a super system. Not just a normal system, but a super system. So if we combine both of these blocks into one, how much would it weigh? It would weigh exactly super would equal 4.5 kilograms plus 2.5 kilograms, 7 kilograms. Okay, and what do we know? We know that there's actually only one net force acting on this, only one relevant force acting on the super system, which is the force of gravity. Now you might ask, why are we drawing it this way? I don't know. You could draw it anyway. I was just thinking of it as if, because this is a whole system, right? And we imagine like the block was still on the table. Oh, we probably don't want to draw it this way. I mean, either way, my point is that there's only one actual force acting on it, which is the force of gravity of the hanging mass. And that is hanging mass equal to 2.5 kilograms times 9.81. So equal to negative 24.525. And actually here it doesn't, just be careful with your unit, like your pluses or minuses. But we know that this is the net force acting on the whole system, 24.525 newtons. And if we want to find the acceleration, we just use this handy formula. I'm actually going to omit the minus here. Actually, no, we shouldn't. It makes sense here. Newtons times acceleration. So acceleration is equal to negative 3.5 meters per second. And one more thing, I forgot to draw my Rosetta again. I guess, which way would it be really? Like I wouldn't be too sure to, like, how would I say which direction acceleration is moving, because like of the whole system, well, let's just say the magnitude. That is 3.50 meters per second squared. Now we want to calculate the tension force between the two blocks. So we're trying to find the tension force. Now, in order to do this one, we should be looking at each individual block. So if we look at the hanging mass first, so FBD of hanging mass. What do we know? There's gravity pulling down, and there's a string pulling up. Okay, and we're trying to find how hard that string is pulling. We know that gravity is equal to 2.5 times 9.81. So that's negative 24.5 plus force of tension. And what do we also know? We know the acceleration of the whole system, so we know how quickly this mass is also accelerating. They move as a whole, right? They're connected by a string, so the acceleration is the same for each individual block. So acceleration is negative 3.5 meters per second squared times our mass of 2.5 kilograms. Is it still possible to see? Oh my, I'm blocking it. It's fine. It's just math from now on, so there's nothing very important to see anyways. So negative 8.75 newtons is equal to negative 24.5. Let's just bring that over, really. Plus 24.5. 15.75. So 15.75 is equal to our force of tension. Great. So we have solved the last question, which is that the tension force, 15.75 or more like 15.8 newtons. Wow. That was a long one. And I am tired. Yeah, I didn't realize that. Why did it take so long to make this video? I don't know. But I hope that you guys learned something. Yeah, I feel like it shouldn't have taken that long. There was like, what, 5 questions, but, you know, I might have gotten a bit distracted. But I am tired. And that's okay. Yeah, I hope you learned something from this video. I hope you had fun. And most of all, I hope you had fun. So, that's it. Bye-bye.